All right, I'm connected. I will now turn off my video. On Friday, maybe I will, well, we'll see. Maybe there will be something I can do with that video. Please join from my other device. Start the meeting. Continue. Okay. Go to share screen. All right, so it turns out that Zoom is no good at figuring out what is my face and what isn't. Because if I try to turn on the virtual background, it thinks that my glasses, teeth, part of my hair, well, now this is good. It got rid of some of the fat on my cheeks. So yeah, it turns out that Zoom is not good at figuring out what is me and what isn't. And I think it's because I'm not using a non-uniform background. I mean, I'm not using a uniform background. I should really be using a green screen. But this was great fun on Saturday during my Dungeons and Dragons game. I could put on this background. Any guesses as to what this background is? Anyone? No guesses? This background is actually a map of Mars. It's an elevation map of Mars. And I have an elevation map of Mars with various location markers in it because at one point I had the ambition to start working on a novel about Mars. And one would think that during quarantine, I would be able to work on that, except no time during quarantine. I still have work and actually a bunch of things, both with work and personal life, got busier. Okay, enough of that. Let's turn off the psychedelic background. It is 10 o'clock. Let's start discussing physics. First of all, nothing will stop me from discussing books. This is a really good book by a guy named Steven Strogatz. He's a mathematician. It's called Nonlinear Dynamics and Chaos. And it walks you through, on a more advanced level, the mathematics of chaos, which you may have heard of. Chaos is basically the phenomenon of differential equations with solutions that oscillate, but they don't oscillate with a steady period. They oscillate non-linearly, sometimes rapidly, sometimes slowly, and there's no easily predictable pattern. And this is a book that really makes sense of that. It makes sense of it in terms of some very nicely visual analogies. And it is the classic book. Now, it looks like the hardcover latest edition is expensive as all hell, but there are older editions and there are paperbacks. So I highly recommend it. All right. Here's what we're going to discuss today. We're going to talk about diffraction by two finite slits. Let's go back to Young's two-slit experiment. All right. Before, when we were discussing Young's two-slit experiment, we assumed that the slits were very tiny. But in fact, of course, they have finite size. And if we look at the diffraction pattern that people get in experiments, well, we see a bright spot in the middle. We see alternating bright spots that slowly get dimmer. And that makes sense because, of course, the spots up here are farther away from the slits than the one here. So the light that gets up here, no matter which slit it comes from, is going to be fainter than the light that gets here. Now, maybe those two faint paths will interfere constructively, maybe destructively. But if they do interfere constructively, well, we're adding two faint things, whereas here we're adding two strong things. So all that makes sense. Here's what doesn't make sense. You see how it starts off bright, gets dim, gets really dim, then gets brighter again? That's what we want to make sense of. All right, that's the thing we're going to try to understand. And so we have to do a more detailed calculation than we did last time. All right, remember with two tiny slits, steady oscillation. With one finite slit, we got oscillation and decay. Now we're going to do two finite slits. So we're just going to add up light going on all of the different possible paths from anywhere on this slit, anywhere on that slit, to some detector far off at infinity. All right? And of course, if we were to take a reference path from the center and say that the center is at y equals 0, then the phase leg between, let me get my annotation, let me get my annotation tool if I can. The phase leg between this path and say this path would be this down here, which is y, oops, that should be a y, sine theta. All right, so we're basically just adding up a whole bunch of paths that differ by y sine theta, except that we're only adding some paths. There's no path from here to the detector. I mean, we've drawn a reference from here, but that's just a geometrical reference. We're just drawing a line. It might not be a line that you can actually travel on, all right, but we're just measuring everything relative to that line. Light could travel along this line, light could travel along this line, light could travel along this line or this line. But we're going to measure all those paths that light could take relative to this line. It's not a path that will actually take. All right, and let me get rid of all of that. Okay, so I'm getting rid of my annotation tools. All right, well, we could break that up. We could write that as an integral over the top slit of e to the iky sine theta from y equals minus a over 2, which is the, d over 2 minus a over 2, because the center of this slit is at d over 2. This is a over 2 below that. This is a over 2 above that. And then the center of this slit is at minus d over 2. This is a over 2 above it. This is a over 2 below it. So we've got this integral over this range of values of y. And then we've got this integral, which is the same integrand. There should be a dy there, over a different range of y values. And let's do some u substitutions. Let's say that everywhere in the top slit, y is d over 2 plus delta y1. And in the bottom slit, y is minus d over 2 plus delta y2. Well, if we do that, these exponential factors turn into a product of two functions because we're adding these two things in the exponent, and adding exponents is the same as multiplying exponentials. So we get e to the ik d over 2 sine theta. That's one of our factors. And then we get e to the ik delta y sine theta. And down here we get e to the minus ik d over 2 sine theta times, again, e to the ik delta y sine theta. And so we break all of that up, and we've just got this exponential factor times this integral plus a different exponential factor times the same integral. All right? So you got the sum of two exponentials multiplied by this integral. Now we know what the sum of these two exponentials is. It's proportional to cosine of kd over 2 sine theta. And we know what this integral is. We did it last time. And we got something that's proportional to the sinc of ka over 2 sine theta. And somebody must have a question because I've thrown a lot at you. We've set up a lot of notation. Anyone? Anyone? Really? This is all perfectly clear? Absolutely clear, no questions? Okay, well then let's look at these patterns in Mathematica. Oops, let me go back to there. Go to there. These Mathematica files that I'm using today are all on Blackboard. So we've got two different, we've got a notebook that has two different things for finding the diffraction pattern of two slits. If they're very narrow slits, we use this function. It's just 1 plus that cosine, which is the same as the cosine squared of something else, because I'll write it here. Remember that 1 plus cosine of x over 2, this is a trig identity, equals cosine of x over 2, whole thing squared. And really, I should be doing it like this if I'm going to do it in Mathematica, so that we have something like that. And we could even test that, all right? We could take that expression and subtract them, and Mathematica doesn't do much with it, but then we could ask Mathematica to simplify that difference, and it comes out to 0. That's a way of testing your algebra in Mathematica. If you think the two expressions are equal to each other, take one of those expressions, subtract off the other one, put them inside of a simplify command, and if all of the algebra and trig identities cancel out, then Mathematica will give you 0. If they don't cancel out, Mathematica will give you something other than 0. And you may never again calculate diffraction patterns in your life once you're done with this class. But if you're doing any kind of complicated algebra in any sort of science, this is a trick worth remembering. All right, so we've got that sum of two cosines. Sorry, that sum of two exponentials, which turns into 1 plus a cosine or cosine squared of something. And we see that we get this pattern, which does decay, but it decays very slowly because it's decaying as 1 over the square distance from the apertures. And so if we're at a very large angle way out here, an angle close to 90 degrees, we're also at a very large distance. Whereas if we're at a small angle over here, we're at a short distance. And that is why in Mathematica it decays like this. But now let's look at that diffraction pattern of two finite slits. And I'm just going to, this should have been KD over 2. I'm just going to write it like that. Keep everything consistent with what we did in the notes. All right, so let's play around with this. We've got the product of a cosine theta, which is just cosine squared theta, which is, as we derived last time, 1 over the distance squared. That sinc function, which is the diffraction pattern of a single slit, multiplied by cosine KD sine theta over 2. That's the diffraction pattern of a pair of slits, and we're multiplying them. So let's start playing with our variables here. If I play around with I should make this plot range 0 to 1. Why is that not happening? All right. If I make a really large, you see how the central peak gets really small, gets really narrow? And if I make A really small, the central peak gets wide. Right? That's playing around with the sinc function. Let's make A 0. Now let's play around with the spacing between the slits. If I make the spacing between the slits really large, this, by the way, is just the fact that Mathematica has a hard time doing really, really high resolution graphs unless you explicitly tell it to. If I make the spacing between the slits really large, I get that the spacing between the little peaks is very small. And if I make the spacing between the slits small, I get that the spacing between the little peaks is much larger. All right? And if I make this spacing like this, we got an intermediate case. See how as I play with the slit width, the overall peak gets narrower. And if I make the slits really wide, then I can see the center peak, the first peak, the middle, 1 off to the side, 2 off to the sides, 3 off to the sides. And if we really squint at it, we could persuade ourselves that there's something more over here. We'd have to really squint in order to do that. If I make the slits really far apart, then becomes a little more plausible. You see the center, you see the first, the second, the first side lobe, the second side lobe, the third side lobe, the fourth side lobe, and if you really squint, you might persuade yourself that there's something here. So what do we want to take away? First of all, we want to take away that when we do this calculation, we get the product of two functions, and it looks just like what we saw earlier in the experimental data. All right, this product of two functions really does look, at least qualitatively, like what's in here. And if you were still doing labs, then you could perhaps do an experiment to verify that. The second thing to notice is that when we multiply two functions, we get the sinc function, which is oscillating like this, and then we get the cosine squared kd over 2 sine theta, which is oscillating more rapidly. And we know that in the, whoops, that's not the file I wanted. We know that this pattern is due to the slit width because when we change the slit width, the overall spacing of the spikes doesn't change. Right now you don't see any spacing between the spikes. I'm going to change the horizontal scale, sort of zoom in so that you can see the spikes. When I play with the slit width, the spacing of the spikes doesn't change, but this thing that we call the envelope function modulating the spikes. And it's called the envelope function because it's sort of around it and on top of it. You've got the spikes, and those spikes are inside of or covered by this more slowly varying function. And we say that the effect of the aperture size produces a slower variation because, well, look at it, all right? The pattern that changes when we change the aperture size, it has a peak here and has another peak there. The pattern that changes when we change the spacing between the slits or the spacing between the apertures, it has a peak here, a peak there, 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 and so forth, all right? So what we're noticing is that when we change the large feature, all right, the spacing between the slits, which in the actual geometrical image of this two-slit experiment is the big thing. When we change the big thing, on the diffraction pattern, we're changing tiny features. Whereas when we change the little thing on the diffraction pattern, we're changing the big features, right? And that's a more general thing. That's a much more general thing in physics. This isn't just in two-slit experiments. It's anytime you send in waves and use those waves, anytime you send in waves and scatter them off of something, and look at the diffraction pattern. And I think that what I'll do is I'll switch to freehand and share my screen and switch to OneNote. There's a very important application of this stuff in X-ray diffraction. So why is, okay, there it is, it's showing up now. So proteins, important molecules. By the standards of molecules, they're large. They could be made of hundreds or thousands of atoms. But by the standard of the real world, or the world we live in, by the standard of human experience, they're very tiny. So we can't look at them directly. A protein molecule may be a bunch of atoms that are joined up with each other in some very elaborate configuration like this, okay? I'm just drawing whatever weird shape right now. Okay, so this could be a protein molecule. Well, we can't see that with visible light. It's way too tiny to see with visible light. And what we do is people will make a crystal of that, which means they'll just have a bunch of these all lined up. All right, they'll just have a bunch of these. And I just picked whatever weird shape without even thinking of it. I'm not going to try to replicate that. Let's have something that looks like a crescent moon. That would be a nice pocket for something to fit into. You put that on the cell membrane, it would be a pocket something could fit into. And then if it fits into that, it would change, it would trigger a chemical reaction. So they arrange a whole bunch of these periodically. Right? And they need to arrange a whole bunch of them, because if you just scattered X-rays off of one of them, well, you're not going to get much signal out. All right? Good luck getting a signal. Good luck getting a detectable amount of X-rays off of one of them. So people arrange a whole bunch of them, and they arrange them periodically, okay? So this is a crystal. It may not be the kinds of crystals you're used to thinking of, stuff like sodium chloride or something, but this is a crystal. And they shine X-rays on it. And they're going to get a very complicated pattern of spots on the screen. Right? And the very small features, the small features here, if D is the spacing between the protein molecules, then this will be proportional to 2 pi over D in the diffraction pattern. Whereas the spacing between atoms, we'll call that A, that will be the bond length, the spacing between atoms. That's going to determine whether this one is brighter than that one, okay? So determining whether these two brightnesses are the same or different, that's going to affect the relative brightness of features that are 2 pi over A apart. And people do this every day. I'm giving you the crudest possible explanation of it, but people do this every day to do study the structure of protein molecules. They're not really just interested in measuring one bond length. They're interested in measuring all of the bond lengths and all of the bond orientations in this protein molecule. Because if they can measure all of the bond lengths and all of the bond orientations in the protein molecule, then they know the detailed atomic structure of the protein molecule. And if they know the detailed atomic structure of the protein molecule, then they can ask things like, okay, what other protein molecules could attach to this? Or maybe it wouldn't be a protein. Maybe it would be a sugar. Maybe it would be a fat or a lipid or a vitamin or some other kind of signaling molecule or whatever. but they can ask what other kinds of molecules will attach to it. And they can look at the details of it, and they could say that, okay, over here on this feature, this is positively charged because it's got something that tends to ionize when placed in water. Well, if that's positively charged, then it's not going to interact with, say, sodium ions, but it might interact with chloride ions, or it might interact with a protein molecule that has a negatively charged thing on it. They might look at this over here and say, okay, based on the way that all of those molecules are arranged, this part is fatty. This part is hydrophobic. And if it's hydrophobic, then anything that's hydrophilic is going to stay away from it. That will tell them something about how this part of the protein molecule interacts with other molecules. So that's where these things come in. That's where these diffraction patterns really matter. It's not just looking at two slits. Looking at two slits was important for establishing the nature of light, and there are still some people who do more sophisticated versions of the two-slit or three-slit experiment to study the nature of light on the quantum mechanical scale. But on a day-to-day basis, people aren't looking at the two-slit experiment. What they're looking at is diffraction by protein molecules, by crystals of protein molecules, or crystals of materials that they want to study in the lab for engineering applications. I guarantee you, by the way, that right now there are a whole bunch of X-ray crystallographers that are looking at the proteins that are produced by the COVID-19 virus. I guarantee you that there are people who are already, if they haven't yet put them in front of X-rays, it's only because they haven't learned how to crystallize them yet. But as much as people are being told to stay at home, I guarantee you there are people who have been given exemptions from that. These would be the people who know how to express the molecules, to take the RNA sequences in that virus, translate those RNA sequences into protein molecules, and then get those protein molecules to crystallize so they can stick them in front of X-rays and do this kind of structural work. Those people are working very hard right now. All right, so let's go back to our notes. All right, so what we learned was that when we have two slits, we get that the diffraction pattern is the product of two functions, one of them depending on the large scale features, the spacing of the slits, or as you'll learn in a protein, as we discussed in a protein crystal, the spacing of the crystalline units. Then there's another function that depends on the small scale features, the size of the slits, or the details of the protein molecules. Right? And we call the thing that depends on the small scale features of the actual object the envelope function. And the envelope function has zeros whenever k over 2 sine theta equals pi. So it has zeros when sine theta is lambda over a, or 2 lambda over a, or 3 lambda over a, and that just comes from setting k, from remembering that k is 2 pi over lambda. And then we've got these smaller features. Those show up, these little nodes show up when kd over 2 sine theta is an integer multiple of pi. And so that gives you sine theta is lambda over d, or 2 lambda over d, etc. Any questions so far? Anyone? Again, large scale features of the object lead to small scale features of the diffraction pattern. Small scale features of the object lead to large scale features of the diffraction pattern. And in real life, you're not going to spend your careers looking at two slit experiments unless you're doing certain things in quantum optics. But this is just a warm-up version of what you'll really do. What you'll really do is X-ray diffraction. And by the way, if you want to learn more about that, talk to Dr. Morales, the department chair. He's working with a few faculty in chemistry. Catherine McCulloch is an X-ray crystallographer, and she's a biochemist and X-ray crystallographer. So if you're interested in seeing this stuff in some context that's a little more applicable than the two-slit experiment, talk to her. But this sets up all the mathematics that leads to it. All right, more generally, I've been hand-waving and saying small-scale features lead to large-scale features, small-scale object features lead to large-scale diffraction pattern features, and vice versa. Here's a more general proof. Let's take a whole bunch of slits. And for each slit, we'll say that Y1, Y2, Y3, etc. is the center of that slit. And then each slit goes from minus A over 2 to plus A over 2. Now, this is one thing that wouldn't be true in the X-ray case, okay? In the X-ray case, there's going to be more than one type of atom. Each atom would scatter with its own strength, and each bond would have its own length. And so that's going to make the real pattern much more complicated. But let's do the three-slit experiment. We're going to get another sinc function, sinc of k over 2 sine theta. And then each sinc will be multiplied by e to the I k times the y coordinate of that slit in sine theta. So we're going to get e to the minus ikd sine theta plus e to the ik times 0 times sine theta, and e to the plus ikd sine theta, right? Which is just a slightly more complicated function. And let's plot that in Mathematica. Open a different notebook. All right, and here, what I want you to notice is that we get something that's a bit more complicated than before. It's got a tall peak, a short peak, a tall peak, a short peak. I left out the sinc function. Right? And I just realized that I misnamed things. So let me fix that. And I left out the sinc function. If I leave out the sinc function, what kind of situation am I studying? Anyone? Well, what's sinc of 0? Okay, let's just test that. Sinc of 0 is 1 because sine of x over x goes to 1. All right. So if I have no sinc function in there, that's the equivalent of not multiplying by the sinc function. Leaving it out is the equivalent of multiplying by 1. So I must have k times a times sine of, here's how you do theta in Mathematica. All right, we're going to play with this D0, D10, 50. All right, and we're going to say that. So what I've just done is I've just defined a function that is the product of everything we had in the calculation I showed here. In the calculation here, we've got 1 plus e to the ik something plus e to the minus ik something. E to the I something plus e to the minus I something is 2 times the cosine of that something. So that's what we would get in the 3-slit experiment. And then I just start, there is something wrong here. I never hit Shift Enter. And because I never hit Shift Enter, what now? I'm sorry, there is something wrong with this. You know what it is? I never told it that A is also an input in that definition. Okay, this is what I get for trying to do things on the fly. So if A is 0 and D is non-zero but small, we get this function, which has small peak, large peak, small peak, large peak. All right, which is just what we had before. And right now we've got A is 0, so the sinc function is 1. Then as I make A non-zero, we again see the same pattern as before. We see that changing D, the spacing between the slits, just changes the spacing of the spikes. If D is small, you can resolve individual spikes. If D is large, you can't. Changing A, well, if A is small, we don't see that decaying envelope. Whereas if A is large, on the medium, if A is somewhat small, we can see the central peak and a secondary peak. And as we make A larger, we go from seeing the central and secondary to seeing the central, secondary, tertiary, quaternary, fourth. And as we make A larger still, we see secondary, third, fourth. If you squint, you can persuade yourself that it's a 5th peak. So what I want you to take away is that the basic phenomena have not changed. Some of the details have changed, all right? If we look at it close up, if I were to change, let's change the range of angles. Let's express these angles in degrees. Minus theta max to theta max. I'll show you what I'm doing. I'm just going to change the range. It's going to make it possible for us to take theta max anywhere from 1 degree to 90 degrees. So right now here we're looking at from 1 degree to 90 degrees. All right. Here, so we're looking at from minus 15 to 15. You can see large peak, small peak, large peak, small peak. As we change D, it changes the spacing between those. If we change A, it certainly modulates those, all right? You can see that as we change A, we now get large peak, small peak, almost as large peak, slightly smaller peak, less large peak, really small peak, even smaller peak. You see how the pattern goes? You still get these alternating peaks, but these alternating peaks have clearly been multiplied by some sort of sinc function. And I'm going to post this updated file on Blackboard as soon as we're done. Any questions so far? Again, the message is that if you have a 3-slit or 4-slit or whatever problem, you find the pattern of 3 infinitesimal slits just by adding up e to the I k sine theta times the y coordinate of the slit. The a generalization of what we were doing last week. Then, assuming that all of the slits are identical, you multiply by the sinc function. Now, we can do more than just that. Sometimes people put what we call a phase mask in front of the slits. All right, and one possible version of a phase mask is that we put a high index layer in there so that the light gets delayed passing through it. You're already familiar with that notion from when we were doing thin films. The basic idea of it, again, would be this. Let's say we've got two slits, and maybe I'll put a phase mask in front of both of them, all right? And I'm gonna give them both thickness delta X. They're gonna have the same thickness, right? This is done all the time, by the way. You can buy these commercially. And this is gonna have index N1, and this is gonna have index N2. And here's the beauty of it. These indices are changeable, okay? These indices are changeable with electricity. They use a material whose refractive index changes if you apply a voltage to it. And so the number of cycles that a wave goes through up here, if it just makes one pass through, we're not doing round trips. This section is phase mass. The number of cycles on one pass is going to be equal to d over lambda over n2. Oh, sorry, n1, my bad. And 1 over n is n1, so you get n1d over lambda. And down here, all right? Now, if both of these had the same refractive index, they're made out of the same material, and we haven't turned on different voltages, then the phase difference, well, in any case, the phase difference will be d over lambda n1 minus n2. So if n1 equals n2, then the phase difference is 0. Everything we've done before applies. But if the phase difference was non-zero because we applied a different voltage down here and up here, then we have a phase difference, okay? Now we've just adjusted the phase between those. And so now we've adjusted our diffraction pattern. Now what we're going to get is e to the I k y1 sine theta e to the I phi1, all right, where phi1 would be 2 pi n1 d, sorry, n1, why did I write d? It should be delta x. And I can erase, so. All right, 2 pi delta x over lambda, and phi2 will be n2 delta x times 2 pi over lambda. Then we're just going to have e to the I ky1 sine theta, e to the I phi1 plus e to the I ky2 sine theta, e to the I phi2, whole thing multiplied by sinc of ka over 2 sine theta. All right, so that's what we've got. Now, why do people do this? People do this because sometimes they want to adjust the phase of the light coming out of here and the phase of the light coming out of there. One reason might be, well, these cool patterns of bright spots can make nice laser light shows, and certainly there are special effects applications of these things. But there's something much more important. In a telescope, all right? In a telescope, everything that we did when we were talking about lenses and mirrors, we were assuming that the light is coming in nice and collimated, and we're assuming that it took the same amount of time to get from the source to the detector along any of these paths, okay? These are parallel paths. They started off up here at infinity. They're gonna meet down here, and they all took the same amount of time. But in fact, there's turbulence in the atmosphere, okay? And because of the turbulence, you got pockets of air with different densities, different temperatures. Some of these paths go through a thicker pocket of air. Some of them go through a thinner pocket of air. So they all take different amounts of time. And so if we put a phase mask in there, then we can control the amount of time that it takes to go through each of these, and we can compensate for that. So we've got a phase mask that compensates for the fact that it took different amounts of time up here. So you clean up your wavefront. This is done all the time in astronomy. It was actually invented, or at least parts of it were invented by the military. I don't know enough of the history to say whether the very first application of this was in the military or in civilian astronomy. What I do know is that once the field was very active, there were things that got done in military research labs that were later independently discovered by people doing basic civilian astronomy. This is also done in biomedical optics because, of course, light takes different amounts of time to go through different parts of the tissue. And so people are now using that in microscopy. All right. Any questions? Anyone? All right, so we can go and we could put phase masks in front of one or both slits, and we could adjust our diffraction pattern. We could replace the factor of e to the I k d over 2 sine theta with a factor of all that multiplied by e to the I phi and adjust the light. We could do a 4-slit pattern. And if we don't have any phase masks in here, then the 4-slit pattern would be very simple. The 4-slit pattern would be a sinc function because we're assuming 4 identical slits multiplied by e to the I times k times sine theta times the y coordinate of each slit. One of these has y coordinate d over 2. One of these has y coordinate 3d over 2. One of them has y coordinate minus d over 2. And one of them has y coordinate minus 3d over 2. And so when we add all of those up, we get a sinc function out there multiplied by the sums of these exponentials. And the exponentials come in pairs. You got e to the I something and e to the minus I something. E to the I times something else, and e to the minus I times that something else. So we get the sum of 2 different cosines, because this is 2 cosine of something, this is 2 cosine of something else. We add up those 2 cosines. And I'm going to have you do a few exercises like that on next week's problem set, or I guess it'll be 2 weeks from now, because next week is spring break. So I'm going to have you do problems like that where you play around with the diffraction patterns of different kinds of slits, different patterns and combinations of slits, and see what happens. Finally, There's an alternative way of doing this. I've been adding up so far the diffraction patterns of slits and taking advantage of the fact that if they're all the same size, then in each case we're multiplying by the same sinc function. But I don't have to add up a bunch of different integrals. I could have one integral going from the very bottom of the system down here to the very top of the system up there. And if I just have that one integral, then I could say, well, sometimes the integrand is non-zero. It's 1, like here or there. And other times it's 0, like here or here. Or here's the beauty of it. In other places, if I put a phase mask here, I could say that here the integrand is neither 0 nor 1, but rather e to the I phi. So I would be taking this e to the I ky sine theta and multiplying it by a function that would be 0 here and here. It could be 1 in any unobstructed slit, and it could be e to the I phi if I put a phase mask in front of it. And in general, when you have an integral where you take e to the I e to the I something times y, whatever variable you're integrating over, multiplied by a function of that variable, that's called a Fourier integral or a Fourier transform. And we're going to see a lot of those next fall in math methods. All right. I've thrown a lot at you. Someone must have a question in this final minute or two. Anyone? All right, if there are no questions, then I'm going to log off. As always, if you have questions on the problem sets or the upcoming homework assignments, you can reach me by email. We can set up Zoom chats. On Friday, we're going to talk about diffraction gratings, which are devices used to break light into spectra and see how much light of each type you've got. And then we'll have spring break, which will not be much of a fun break going out and doing stuff. Then the week after spring break, we're going to do a few more things with diffraction and imaging, and then we will start relativity. Have a good day.